Hello students and welcome. Chalo, today we're going to tackle a very important and actually very interesting topic from your Unit 3 Current Electricity. We're going to learn all about electrical energy and power. And don't you worry, we'll go through it in an ekdam simple way that will be completely exam safe and, I promise, very easy to remember.
Acha, let me ask you a quick question. You've all experienced this, right? You plug in your phone to charge or you're using your laptop, and after a while you touch the charger or the adapter and it's warm. Sometimes it's even quite hot. Ever wondered why that happens? Well, that heat, that's not a bug, it's a feature. It's physics right there in your hands, and it's the key to understanding our whole topic today.
So how do we get our heads around this? Instead of jumping straight into all the complicated physics definitions and formulas, let's start with a simple story. A little analogy that will make everything just click into place. Are you ready? Let's do this. I want you to just close your eyes for a second and picture this. There's a person. That's our hero, the electron. And this person is trying to run from one end of a super crowded market to the other end. You know, like a busy Sunday bazaar. Can you see it? Okay, good. Now let's break this picture down. That runner, of course, is our single charge, the electron. Now what's making him run? There's a constant push from behind, forcing him through the crowd. That push is our voltage, the potential difference. And the crowd itself? All those people getting in the way, making it difficult to run? That's the resistance of the wire. So what happens when our runner bumps and jostles and collides with people in the crowd? Well, there's commotion, there's friction, things heat up. That chaos, those collisions, that is the heat energy being dissipated. Simple, isn't it? Okay, perfect. Now that you have that crowded market story fixed in your mind, we're ready to look at the official language of physics. Let's see what the NCERT textbook says, and you'll see how our little story makes it all make sense. First up is electrical energy, which we write as delta W. The textbook definition is the energy dissipated as heat in a conductor during a time interval delta T. Now think back to our market. This is the total commotion, the total chaos created by our runner over his entire journey from one end to the other. And the formula to calculate this total heat is delta W equals current, I, times voltage, V, times the time interval delta T. So then, what is electrical power? Power is simply the rate at which this energy is being used up, or dissipated. In our market analogy, it's not about the total commotion anymore. It's about how fast that commotion is happening. How many collisions are there per second? How much heat is being generated every single second? That's why the formula for power, P, is just energy, delta W, divided by time, delta T. And if you do the math, that simplifies beautifully to P equals I times V. Now, this is the really cool part. From our one base formula, P equals IV, we can actually build two more super important formulas. You just need to remember our good old friend Ohm's law, V equals IR. So let's take that and substitute it for V in our power formula. P becomes I times, instead of V, we write IR. So that's P equals I into R, which gives us P equals I squared R. That's our second key formula. Now, let's go back. We can also write Ohm's law as I equals V by R. Let's substitute that into our base formula, P equals IV. We get P equals, instead of I, we write V by R times V. And that gives us P equals V squared by R, our third formula. See, they are all connected, just different ways of saying the same thing. So listen carefully. This is absolutely crucial for your exams. You must know all three of these power formulas by heart. P equals VI, P equals I squared R, and P equals V squared by R. When you're solving numericals, you'll need to pick the right one based on what information the question gives you. So learn all three. Let's do a tiny little example just to see how easy this is. Imagine a question gives you the current, I, is 2 amps, and the resistance, R, is 5 ohms, and it asks you to find the power. Okay, so you look at your three formulas. Which one has I and R in it? The second one, of course. P equals I squared R. So we just plug in the values. P equals 2 squared times 5. That's 4 times 5, which gives us 20 watts. See? It's that simple. Okay, Chalo, now let's tackle a very common area of confusion. This is where many students make silly mistakes and lose easy marks in the exam. They get mixed up between energy and power. Let's clear this up once and for all. Just look at this table. It makes it so clear. Energy is the total amount of work done. Its unit is joules.
Power, on the other hand, is the rate, how fast that work is being done. Its unit is watts, which is really just joules per second. Here's the best way to remember it. Think of your home's electricity bill. The final bill that comes at the end of the month, the total amount you have to pay, that's like energy. But right now, if you go and switch on a big AC in the water heater, and you look at your electric meter, you'll see its little disk spinning very, very fast. That speed of spinning, that is power. So, to make sure you never ever forget this, just burn this one little trick into your memory. Power is how fast energy is being used, and energy is how much total energy was used. Simple, right? How fast versus how much.
Okay, so we've got the formulas and we know the difference between energy and power. But you might be thinking, sir, why does all this matter in the real world, outside of my physics exam? Well, let me tell you, this concept isn't just for exams. It's the fundamental reason how our entire modern world gets its electricity. Yeah, seriously. This idea of power getting dissipated as heat is the absolute key to understanding how electricity from a power station maybe hundreds of kilometers away can travel all that distance and reach your house without just fizzling out on the way.
Think about it. Those massive power lines stretching across the country. They are made of metal, so they have some resistance, right? Let's call it RC. This means as current flows, some power is going to be lost as heat. How much? Well, we have a formula for that. Power lost, PC, will be I squared times RC. Now, to send electricity efficiently, we want this loss to be as small as possible. We can't really change the resistance of the wire. It's miles long. So the only thing we can control is the current, I. We need to make the current as small as possible. But wait a minute, how can we send a huge amount of power with a tiny current? That's where our other formula comes in. P equals V times I. If we make the voltage V incredibly high, we're talking thousands of volts, then we can deliver the same amount of power P with a very, very small current I. And that is exactly what is done. That is the reason you always see those danger high voltage signs on transmission towers. It's all about reducing that I squared R loss.
Chalo, we are almost at the end now. Let's do a quick recap. Let's summarize the most important points from this chapter that you absolutely must have on your fingertips for your exams.
Right, here are your key takeaways. Number 1, why is there heat? It's because charges collide with the atoms in the conductor. Number 2, electrical energy is the total heat generated, and its formula is IV delta T. Number 3, electrical power is the rate of heat generation, and you need to know all three formulas: IV, I squared R, and V squared R. And finally, number 4, never ever mix them up. Power is the rate in watts. Energy is the total amount in joules.
And I'll leave you with one final question to think about. We've just spent all this time talking about how heating and transmission wires is a power loss that we try to minimize. But then, what about devices like your electric toaster, or a water heater, or an iron? How did these things take that exact same loss and turn it into something useful for us? It's a great question, isn't it? Think about it, and we'll explore that in our very next topic. All the best, everyone.